Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1921. The scientific world grappled with a profound enigma. Classical physics, the bedrock of centuries of understanding, found itself increasingly at odds with a nascent quantum theory. One of the most glaring points of contention concerned the behavior of atoms within magnetic fields. The prevailing classical model, rooted in the smooth, continuous principles of electromagnetism, predicted a very specific outcome, which clashed head-on with a bold new theory. Early quantum theory, still in its formative years, offered a strikingly different perspective. It posited a concept so counterintuitive, it initially sent shivers down the spines of even the most seasoned physicists. It suggested that the angular momentum of an atom, which in the classical view could assume any orientation with respect to an external magnetic field, was actually quantized. That is, it could only take on a discrete set of orientations. This was known as spatial quantization, or space quantization. This meant the magnetic dipoles of atoms, when placed in a magnetic field, would align themselves in only a finite number of specific directions. The directions were not a continuous range, but rather a select group derived from the quantum rules themselves. Testing this prediction presented a formidable challenge. The magnetic moment of an atom is incredibly small, and therefore the forces exerted by a magnetic field would be minuscule. To observe the effects of spatial quantization, an experiment needed to be exquisitely sensitive and capable of isolating individual atoms. This is where Otto Stern and Walther Gerlach entered the picture. Stern, a brilliant experimental physicist who had already made notable contributions to the measurement of atomic velocities, teamed up with Gerlach, a skilled experimentalist with expertise in atomic physics. Their collaboration resulted in a seminal experiment designed to test the bizarre but compelling predictions of early quantum theory. The goal was to directly observe the spatial quantization of atomic magnetic dipoles. The experiment's core apparatus was brilliantly simple, yet profoundly effective. It began with an oven, heated to a high temperature, to vaporize a metallic element. The chosen element was silver, due to its convenient atomic properties. The vaporized silver atoms then emerged as a beam, traveling through an inhomogeneous magnetic field. This field, the workhorse of the experiment, was carefully shaped to exert a force on the magnetic dipoles. The field's inhomogeneity introduced a differential force, meaning the force's strength depended on the atom's orientation. The experimental setup next included a detection screen, placed to receive the beam of silver atoms after they passed through the magnetic field. If classical physics prevailed, the atoms, with their continuous distribution of magnetic dipole orientations, would experience a range of deflections. This would then produce a continuous smear or band of atoms on the detection screen. The beam would spread evenly, reflecting the classical expectation that the angles of the dipoles would assume a continuous range. However, if spatial quantization was true, the outcome would be dramatically different. The silver atoms, their magnetic moments restricted to discrete orientations, would be deflected into a finite number of distinct beams. The screen would show a corresponding pattern, a series of separate, discrete lines. The most straightforward prediction, assuming the simplest possible spatial quantization, was that the silver atom beam would split into exactly two lines. This stark contrast between the classical prediction and the quantum theoretical prediction made this experiment a crucial test. The experiment's design held a deep elegance. The oven provided the source of atoms. The magnetic field offered a precise probe. The detection screen furnished the final readout. The entire apparatus operated on principles readily explained, yet capable of revealing a profound discrepancy between classical expectations and the revolutionary implications of early quantum theory. It was now up to Stern and Gerlach to execute the experiment and reveal how the world truly worked at the atomic level. The Stern-Gerlach experiment's results arrived with exquisite clarity. The anticipated splitting of the silver atom beam into distinct lines, a direct manifestation of spatial quantization, was observed. The screen displayed a distinct pattern. The silver atoms, traversing the inhomogeneous magnetic field, separated into discrete bands, unequivocally confirming the fundamental quantum mechanical prediction. This outcome was not merely supportive, it was a decisive validation of spatial quantization. It directly challenged the classical viewpoint, which predicted a continuous smearing of the beam. The precision of the experimental setup allowed for careful data analysis. The deflection patterns, the spatial separation of the atomic beams, were meticulously measured. The magnitude of the deflections correlated directly with the atom's magnetic moment and the strength of the magnetic field's gradient. Through meticulous measurement, Stern and Gerlach quantitatively demonstrated that the magnetic moments of the silver atoms aligned themselves solely along specific, quantized directions relative to the applied magnetic field. This alignment could only occur in a finite number of orientations. The data obtained demanded a theoretical interpretation anchored in the burgeoning Boas-Sommerfeld model. This model, extended and refined by various researchers, incorporated the concept of quantized angular momentum. In this context, each atom possessed an intrinsic angular momentum, a fundamental property of the atom itself. This intrinsic angular momentum was itself quantized in its spatial orientation. The silver atom, with its single valence electron, revealed a magnetic moment, a direct consequence of its electrons. The splitting observed was not into a multitude of subbeams as initially envisioned under certain extensions of the Boas-Sommerfeld model. Instead, it split into exactly two beams. This dichotomy represented a profound conceptual leap. It unveiled the intrinsic angular momentum of the atom's electron and, in so doing, hinted at the existence of the electron spin, a property that had, at that point, no theoretical framework. The spin, a purely quantum mechanical concept, presented itself as a previously unanticipated internal degree of freedom. The implications were broad, suggesting the need for a more complete model of atomic structure. The experiment's immediate impact was substantial. It offered a definitive proof of the concept of spatial quantization. This spurred the development of quantum mechanics. It spurred the evolution of theoretical understanding of atomic structure. It provided a concrete experimental validation of the quantum theory's foundational postulates. It quickly altered the scientific landscape. The results of the experiment were quickly disseminated. They were widely discussed. They proved of central importance to theoretical physicists. The Stern-Gerlach experiment fueled substantial theoretical development. Werner Heisenberg and Wolfgang Pauli seized upon the results and the implications of the experiment. They developed the concepts of electron spin and the Pauli exclusion principle. These theoretical advancements provided a more complete picture of atomic structure and behavior. The success of the experiment accelerated the development of quantum mechanics, leading to new interpretations of previously enigmatic phenomena. The experiment exerted a direct influence on subsequent experimental work. The Stern-Gerlach experiment and the developments it triggered provided the basis for numerous experiments that probed the structure of matter. These included the investigation of the magnetic properties of other atoms and the study of the interaction of atoms with external electromagnetic fields. These experiments helped to refine the concept of electron spin. They also contributed to a deeper appreciation of quantum mechanical principles. The enduring legacy of the Stern-Gerlach experiment is multifaceted. The conceptual framework it provided is an unassailable cornerstone of quantum mechanics. The experiment also finds continued use in physics education. It demonstrates the fundamental tenets of quantum mechanics to new generations of students. The principles underlying the Stern-Gerlach effect have also led to the development of advanced technologies. Magnetic resonance imaging, known as MRI, relies on the same principles of spin precession electric field to generate detailed images of the human. Furthermore, the work by Stern and Gerlach offered a model. It offered a path to understanding and manipulating matter at its most fundamental level. The experiment's influence extends beyond the realm of physics. It spurred technological innovation. The conceptual importance of spin, a phenomenon revealed and validated experimentally, remains a fundamental concept in contemporary research. The Stern-Gerlach experiment transformed our understanding of the atomic world. It gave us tools of extraordinary explanatory power. It offered a gateway to modern technology. The legacy of the experiment resonates throughout physics and beyond. It demonstrates that the pursuit of knowledge, even at its most abstract levels, can yield profound consequences. The experiment itself remains an iconic example of the interplay between experimental observation and theoretical understanding. The findings continue to serve as a testament to human curiosity and ingenuity.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.